So thanks a lot for asking to talk here, and thank you for coming, everybody. So the talk is going to present some results that I obtained with collaborators, and in fact, I will be listing them as we go along during the time of the collaboration with the grant. Now, what you will see in my talk is this tiny, tiny little bit up here. And all of this stuff, it's really what's going on and what's hidden from today. So you might come after the talk, you might feel like, well, it's not so interesting or maybe not so difficult to work on these problems, but actually there is a lot behind it, and that's why I wanted to show you this picture. So there are three problems that I will discuss. So the first one is probably the one I have worked longer on, and it's about the forward cascade. I will give definitions and so on in a moment, but it's definitely an important topic within wave turbulence in general. The second one is an interesting type of continuation of work that I have done, in particular in NLS, in the periodic case, and it's concerning with the defocusing NLS. So I believe, although there was no written conjecture or anything, I believe that people thought that when you have a defocusing NLS, well, there shouldn't be any kind of blow up or implosion because the energy contained, well, keeps things under control. And I will show how this is not, in fact, the case, following some fundamental work of Mer, Raphael, Seftel, and Rodiansky. And the third problem that I will address, it's a more recent collaboration. Started with my former student, Riccardo Grande. After listening to our talk, I think it was the first meeting of the PIs of this collaboration. Eric van der Heijden was giving a talk. It was on rogue waves. It was mostly numerical experimentation. And so I felt compelled to start working on something more applied because I was part of the collaboration. And so we start putting some mathematics behind that, and I will mention a little bit of this. During the PI meeting this past 3 days, Alberto Maspero gave a much more detailed talk on that. I will only give you the overview. All right, so we start with the first one. This is the forward cascade. And as a sample of the equation that I will be working on, let's take the cubic NLS. And I'm going to assume that the initial data, I'm going to call it U0. And I'm not going to say specifically now, but it's going to be smooth enough. And what I wanted to point to, really stress a little bit more, is that this is a periodic case. So I'm going to be in the torus of dimension 2. And I'm going to call alpha 1 and alpha 2, the two periods. And later on, you will see that it's going to be important, the relationship between these two periods. Now, this comes from physics. There are conservation law. There is the mass up here that it's conserved. And there is the Hamiltonian. As long as you have enough derivatives, this makes sense. And the Hamiltonian has a part which is the kinetic and the potential. And I will be addressing only the defocusing case, which here translates into have a plus sign. Or up here, having +1, right, in front of the nonlinearity. Now, it's a very well-known theorem of Bourgain in the periodic case, that if the initial data is in HS, S, actually in this case, local well-posedness is true for S strictly greater than 0, but here I'm interested in a global solution. So as long as S is certainly greater or equal than 1, thanks to the conservation of the energy, you can go from local well-posedness to global well-posedness. So certainly for the rest of the talk, let's say that we have a smooth enough data, and there is a solution which is continuous in time into HS. By the way, there are results that say that this global well-posedness is also true slightly below 1, and more recent result of Hare and Kwok that in the case in which the torus is rational, or a square torus, in other words, I will give you later the definition, but that means that the ratio between alpha 1 and alpha 2 is a rational number, then the global is also true for S strictly greater than 0. anyway, for today, let's just think about smooth solution. Now, so that we are everybody on the same page, let me define for you what is, in this talk, the energy spectrum. So given UTX, which is global solution of my 2D periodic NLS, the energy spectrum is going to be just the magnitude of the Fourier coefficient square, and K is going to run in Z2 because I'm in dimension 2. All I'm saying can also be in higher dimension, but with conditions, but let me just stay in 2 dimension. And let's, for example, ask the question that says this. Suppose that at time 0, my energy spectrum is localized for small k. So this is, if you want, the green line is the graph. It should be discrete, but let me just indicate it as a continuous graph here. And is it true that later on in time, this blob here that is close to 0, supported near 0, is going to move away from that? So for t very large. So this is the first question. And I learned this question from Bourgain way back many years ago. And one way that he thought about this is the following. So let's look, so that you are interested in what happens to this Fourier coefficient square and whether they move to large k. So let's put this weight in front of the coefficient. So 1 plus k to the 2s, and s is going to be large. If there is a motion from low frequency to high frequency, this quantity here, weighted, stressed by this weight, should grow. And then I say, well, let's sum for all the frequency, and let's take the limit as t goes to plus or minus infinity. So let's study this quantity. If there is a growth of this quantity, then it suggests that things are moving to high frequency. By the way, I want to say that for this part of the talk, there is no probability here, right? Everything is deterministic. Hence, from Bourgain, the question whether the Sobolev norms, higher Sobolev norms, oops, sorry, let me just go back here. The higher Sobolev norms, whether they grow as t goes to plus or minus infinity. I guess the audience here understands that for the Schrödinger, going forward or backwards is the same thing. Let's recognize a few simple facts. The first one is what happens for the linear case. Well, in the linear case, we know exactly how the Fourier coefficient of the linear evolution looks like. It's exactly the initial data multiplied by e to the I t k square. Now, I want to emphasize that when you have a torus that period alpha 1 and alpha 2, well, here, this is not exactly the magnitude of the vector k to the square, but it's some kind of magnitude that has to be scaled with respect to the periods. So this star here indicates here and later the fact that you had to really write it in the right way, depending on the periods of your torus. So of course, in the linear case, well, it's obvious what happens, because when you take the absolute value, this e to the I, absolute value that is 1, and so nothing really changes. Everything is completely stationary. And as a consequence, of course, we knew that before, but anyway, the HS norm is here, it's equal the same for the linear evolution is the same as the one of the initial data. So the linear case is trivial. If anything grows, obviously it's going to come from the nonlinearity. Another fact that we know is that if we set ourselves in dimension 1, so still cubic NLS, dimension 1 now, well, that's an integrable system. So there are infinitely many conserved quantities. The fact that is defocusing allows you to combine all this in conservation law, conserved quantity, conserved integrals. And certainly you can say that the HS norm of this nonlinear solution for S natural number is less or equal than a constant for all times. And is a result of Kepler and Topolov, which really uses the integrability of the system, that you can extend this uniform bound not just for S natural number, but for any S, also fractional. Fact 3 is, well, what happens if we do not impose a boundary condition, the periodic boundary condition? Let's say that you're allowed to spread on the whole plane R2. Then there is a result of Dodson around 2000, I believe 2014, that says that we have scattering in this situation. What that means is that your nonlinear solution U is going to be approximated by a linear solution with a certain profile, u plus, u minus. And so when t goes to plus or minus infinity, the HS norm for s greater or equal than 0 of this tends to 0. Now, since you already discussed before that the linear evolution has an HS norm which is bounded, so when t is very large, you use that to have the bound because you're very close to a linear solution. And when t stays in a bounded domain, in a bounded interval, then you use the fact that there is a maximum because you have continuity with respect to time. And so you have a uniform bound as well in this case. But in general, when you are not in dimension 1, when you do have boundary conditions, then you consider the nonlinear problem, there are results starting with Bourgain and then Sobolev, Planchon, Tsetko, Vishilya, that tells you that the HS norm of the nonlinear solution is bounded polynomially. And for now, we know that the degree of the polynomial is about s. This is not at all sharp. The interesting fact about these results is that everybody here, Bourgain, Sobolev, Planchon, Tsetko, Vishilya, used completely different tools to obtain the same kind of estimate. In fact, the first two, Bourgain and Sobolev, was more looking at the Fourier world, Fourier transform, but Planchon, Tsetko, Vishilya use integration by parts with these modified energies. Okay, so this is an upper bound. We know that it cannot grow more than a certain polynomial, but I consider even a more interesting question whether there is an initial data that evolves and that has the HS norm grow. So what do we know in that context? Well, let's think about the fact that growth we associated, at least in certain sense, to resonancy. So I'm going to move from the problem here, which is my nonlinear original NLS two-dimensional, to first transform into the Fourier coefficient. So you can take just Fourier transform. And here I just normalized a little bit by e to the I t k square. But if you define ak to be exactly that, then you know that ak satisfies an infinite dimension system, in fact, it's a Hamiltonian system of this kind, where omega k is, in fact, the sum and subtraction of k squared minus k1 squared plus k2 squared, and so on. And the minus and plus is connected with the fact that you have a bar here. Now, these two systems are equivalent. One you see in the physical world, one you see in the Fourier world. But if I'm looking for something that grows, I'm going to take a subsystem. I'm going to take the one in which the frequency k, k1, k2, and k3, these are four frequencies, four waves if you want, are in resonancy. So omega k is equal to 0. And if omega k is equal to 0, this e to the I omega k becomes 1. And now I'm looking at this, what I call resonant NLS. So this resonant NLS will accompany me for a while. So just keep in mind that it's the original NLS in the Fourier world, and everything is in resonancy. Okay, then a long time ago, Jim Colliander, Marcus Kiel, Hideo Takaoka, and Terry Tao and I, we concentrated on this resonant NLS, and we tried to see if we could find something that grows. And in fact, we did that. But first, we assumed that our torus were square. But you can also do the same argument by assuming that the ratio between the two periods, alpha 1 and alpha 2, is a rational number. So we call this torus a rational torus. So fix an S, which is greater than 1, fix a small sigma, and fix a large K. Then we can construct an initial data U0, which has the HS as small. But if we wait long enough, a very long time t, then the solution of the resonant NLS is going to grow. It's going to be bigger than your fixed K. I'm not going to go into the telling much about the proof of this, but it's a sort of dynamical system type of approach for this to prove this fact. Now, note that this is for the resonant NLS. It's not the original NLS. But I call these slides going down a bit of mathematical rabbit hole for the following reason. The construction that we did when we assumed that the torus was rational, it cannot be repeated if the torus is irrational. Okay, that construction does not work. On the other hand, later, much later, Giuliani and Guardia proved that, well, if the torus is irrational, but not too irrational, so here I just write if alpha 1 over alpha 2, that's the ratio to period, is well approximated by rational numbers. And I'm not going to go into what do we mean with well approximated. There are some definitions in analytic number theory that tells you what that is. Well, then the result that I mentioned, not the construction, the result that I mentioned is still true in this case. This is done by perturbing the torus. So the construction, you use the one for the rational case, but then if your torus is close, is irrational, but you can approximate it well with rational ones, and then you can extend that construction in some sense. And very, very interesting result by Hani, Posadeur, Tsetko, Viscilia says the following. So when we constructed our solution that had that growth, if we wait this long time t, then what they did in this theorem is to concatenate a bunch of these constructions. But you have to make sure that the supports of these solutions are really separated far enough so that the dynamics doesn't cancel each other from one solution to another. And in this concatenation, they were able to say the following. So assume again that alpha 1 and alpha 2 is a rational number. Fix an x S large and a sigma small. Then there exists an initial data U0, which has the HS norm small. And the evolution of the resonant NLS, let me call it V, grows. In fact, you can find a sequence of times. So basically, it will be this capital T, but you have a bunch of them in your construction. And that goes to infinity. So the Tk goes to infinity as k goes to infinity. And this solution of the resonance set in HS increases logarithmically. OK, again, this is for the resonant NLS and for the rational torus. Now, you might think, well, if Giuliani and Guardia were able to extend our result to tori that are irrational but well approximated, then maybe you can extend the Hani, Posadeur, Tsetko, Viscilia for the irrational that are well approximated. That turned out to be much harder, but it's a work that I'm doing with Nicola Camp. So the result, the theorem, I didn't put it here, but we believe it's true. OK, now what happened in the really fully irrational case when you cannot really approximate that well? So this is work with Alex, Yulin, and Bobby. And it says the following. Well, now suppose that alpha 1 and alpha 2 is really irrational. And fix an S, which is pretty large. Then there is a sigma star, such that if U0 is in HS norm smaller than this sigma star, then the associated solution of the resonant NLS is uniformly bounded. So why is this true? So I wanted to point out the fact that when you are in the irrational case, this is what happens. So this k star is written, so I wrote here in terms of coordinates. So let's say that the vector k has coordinate k1 and coordinate k2. And there is this alpha 1 and alpha 2 in front, which are related to your periods. Now, the resonance set is written in this way. Now, of course, the first one is actually two equations, one for each coordinate. And this one is a scalar part that you can write in terms of first and second coordinates, by the way I wrote here. Now, for simplicity, think about the situation in which alpha 1 is 1 and alpha 2 is just an irrational number. Then when you write these conditions here, you can see that you cannot mix first coordinates, second coordinates, because there is this alpha. Think of alpha to be square root of 2, for example. So this two-dimensional resonance set really splits into two one-dimensional resonance. So the I here, the upper I, stands for coordinate 1 and coordinate 2. So now note that for the 1D cubic resonant NLS, any HS norm is conserved, any. This is typical. I'm going to show you the calculation, but this is exactly because we have 1D and because we have a cubic NLS that is resonant. So what happens in the irrational case is that you split the situation that's typical of 1D cubic resonant NLS into two this 2D situation into 1D. So let me do the calculation for you. It's pretty simple for this fact. I want to make sure that it's clear that it's a resonant NLS. It wouldn't be true, of course, for in general. But on the other hand, we know that the 1D is an integrable system. So something like this, I believe it is related to your conservation law. Anyway, so let me do the calculation. So this is 1D periodic, defocused, cubic, resonant NLS. I'm going to write in terms of Fourier coefficient. So this is the derivative of V, then take Fourier transform. This is the Laplacian. That's why you get k squared. We are in 1D. And this is the nonlinearity. Of course, there is the k equals k1 minus k2, k3 because convolution. And then there is the resonant part. K squared equals k1 minus k2 plus k3 squared. So when I do the DDT and I write the HS norm in terms of the L2 of ds, this is just the derivative order s. Believe me, this is 2 times the real part, and you hit only one of the two. And you plug in the information from the derivative of v down here. Now, of course, from the real, you pass to the imaginary because the I that we have in front right here. And here you replace, of course, the part that comes from the Laplacian immediately gives you that it's a real number. So you take the imaginary of that disappears. So remains only the nonlinear part, which is this. And now when you write down what the system tells you that you should be doing, well, you reduce it to the product k1 minus k2 times k minus k3. So let's say k1 minus k2 is 0, so k1 is equal to k2. If k1 is equal to k2, then k has to be equals to k3. So everything collapses. You get this, which is a completely real number. You take the imaginary, and that's 0. So this wouldn't work if you have a quintic or but in the case of the irrational torus 2D, you can actually do this calculation coordinate by coordinates, and you get the 0. Oh, now, let's go back to the full NLS. That was the resonant NLS. And this is still a theorem of Hani, Posadeur, Zecco, Viscilia, the same paper. And as I say, in their case, they consider rational torus. So alpha 1 over 2 is in Q. So the T2 here is rational. Fix an S, large enough, large. And then sigma is less than 1. So that's a scalar number, sigma that is small. Then there exists a U0. But now, what I want you to note precisely is that this U0, the domain of U0, the space domain, is R cross T2. So R is not the time. R is the space. So what I'm thinking about is the domain is a cylinder. So on one side, you have periodic T2, and then you have the line. OK? So the domain is a cylinder. So there is initial data U0 for the full NLS. Now we are considering the full NLS. That's small. And for its evolution, now this is U, the evolution of the full NLS, you do have this logarithmic growth. So the reason why you can extend from the resonant NLS to the full NLS for the whole dynamics is because you're adding a line, and along the line you have a dispersion. So you can control the dynamics of the whole system thanks to the dispersion along the R. OK, now we did something similar with Nicolas Camp. In the sense we are now extending the uniform bound that you get for the very rational tori to the whole NLS. But again, we had to cross with R, so we still, our domain is the cylinder, because we need the dispersion at least along one direction in order to maintain the dynamics under control. Okay, so that's so as far as I know, we are not able to extend this kind of theorems exclusively staying on the torus, because the control on long-time dynamics is complicated unless you have some kind of dispersion. OK, so just to say a couple of things, we are not, as for now, we don't know exactly where it stands, like in the sense that the theorem of the growth of Hani and Posadeur, Zecco, Viscilia it holds for rational tori. This theorem, which is uniform bound, holds for very rational tori. And we don't really have the exact definition of in which side you fall, depending on irrational the torus is, as for now. OK, now that was all deterministic. Now I wanted to introduce a little bit of probability that you might not see directly here. But as Jalal mentioned, and during the collaboration, Deng and Ani, with a very series of papers that were incredibly fundamental, proved that you can actually, rigorous mathematically, I will say, because already these equations were known in physics before, that you can obtain an equation that allows you to read out this forward cascade, or if you want, energy spectrum, as a solution of a certain equation, which we call four-wave kinetic equation. I wrote this for you here. This is the wave kinetic equation that I will just use for today. And in terms of notation, the F is Fk. When I put a little index down below, this means that I'm evaluating the F and the frequency Ki. And the nonlinear, the dispersive relation in this case is the one of the Schrödinger, and I'm not distinguishing here whether you are in a square torus or not, at the same. So there is a lot of work that has been done in this context in terms of solutions of these equations. And by the way, this is obtained, the equation is obtained by assuming that you are in a weak nonlinear regime for the NLS. And you can think, just for the sake of having in mind the same kind of concept, that this F is nothing else than the expectation of the Fourier coefficient square. And this E here, the expectation, should tell you that there is a probability behind it. So I'm not going to go through the definition at all. But what I wanted to say is that with bin Tran, we show that we can find an initial data, F0. So this is an initial data that, of course, has to be positive, because this is a density, has a finite mass and a finite energy. And the support is some non-empty interior. And when you evolve it, this is the evolution of this initial data. If you consider a ball of radius r, and you look at the energy inside a ball of radius r. So you are not looking at the energy all over the place, but just inside the ball. As t goes to 0, this energy inside the ball goes to 0. So what this is telling you is that things are actually migrating from low frequency to high frequency. So he did some numerical calculation with a postdoc of his. This is Das. And by taking this particular initial data here, so this is a decay e to the minus k squared, and then multiplied by k squared, and taking r, so this is the radius of the ball, more or less 10 units, whatever the units are here, then this is the graph that they found. Just think of one of them. The reason why you have many is because in the wave kinetic equation, there were different constants, and they were looking at a different kind of equation with different constants in there. But just for the sake of understanding the concept, just think of the black line, if you want, with a certain kind of constant that I mentioned here. So this is the total energy inside. You start inside the ball, and you start with some energy. This is what you see at the beginning. But then as time evolves, the energy inside the ball tends to 0. So this is a numerical example of energy cascade. So I gave you two examples of people have studied this energy cascade. The one that was really going back to the concept of Bourgain, looking at the Sobolev norms. And one is the looking at the wave kinetic equation and doing both the analysis, numerical and mathematical. All right, so I'm going to switch now into a different topic. This is even the focus of NLS can implode. So this is some work that did with Gonzalo Caolabora, former student of mine, Javi, who is here, and Jia Shi. And we take the same exact equation that I have been working with. This is defocusing. The one here tells you that you are defocusing. So the sign between kinetic and potential is 1. But I'm in higher dimension now, so dimension 8. And you say, why 8? Well, you will see that in a moment. But just to understand in which setting are we. So we usually classify this kind of equation into energy subcritical, energy critical, energy supercritical. You can also talk about mass, but let's concentrate on the energy. So I'm going to look at the scaling. So this is a scaling, not important where it comes from, but the equation itself has a natural scaling. And the critical scaling, which tells you when you critical is the scaling such that when you take the HSC of the initial data, you cannot shrink it or remains the same, so that you cannot make it small data. Okay. So the critical scaling, it's d over 2 minus 2 over p minus 1, p being nonlinearity. Now, in our case, d is 8. So here you see p is 3. So here it is. So this scaling is 3, which is greater than 1. So we are in a situation in which the problem is considered to be energy supercritical. OK. Now, the expectation was that still, in spite of being supercritical, because you have the conservation of the energy and you are in a defocusing case, you shouldn't really see blow up. For me, the blow up means that finite time blow up means that there exists a capital T such that the limit as little t goes to big T of the ut in L infinity norm goes to infinity. Now, there is a series of papers by Mer, Raphael, Rodiansky, and Seftel. And here I'm going to only concentrate on one of the three, the one in which they consider the NLS. They say that in R8, there exists a spherical asymmetric smooth initial data such that its evolution via the NLS blows up in a self-similar manner at finite time. Remember, for me, NLS is the cubic NLS, OK? And this is in R8. So we are not in the periodic case in their argument. And neither you can periodize it because what they found is a spherical symmetric object. Now, how do they prove this theorem? Well, the theorem goes via the Madelung transformation. And it transfers the NLS into a compressible Euler type or Navier-Stokes type initial value problem. So the Madelung transformation does the following. You start with u, which is a complex valued function. You write in polar coordinates, square root of rho, and then e to the I, the phase, phi t. And now, when you write down the equations, you realize that rho can be considered a density in a system, a fluid system. And v, if you define v to be the gradient of this phi, then you can think of v as being the velocity. So in this way, this was not a new thing. People knew about the Madelung transformation. You can transform the NLS into a compressible Euler-type equation. Now, the theorem that we proved was, well, at least one version of it, replaces R8 to torus of dimension 8. So there exists a smooth initial data such that its evolution via the NLS, the cubic NLS, blow up in a self-similar manner in finite time. Now, what are the ingredients of the proof? Well, the beginning is the same. And I should say that the concept, or the first thing you want to prove here, is move from spherical symmetric to just non-spherical symmetric. And once you've done that, this is in R8. And then once you've done that, you can use cutoff functions and periodize. So the first goal is to prove the same result as Mer-Lenoir, but removing the radial symmetry. So again, you start with Madelung transformation, change into self-similar variable, find a smooth, and this is incredibly important, smooth stationary profile, and prove very good property for this. Then work on the linearized equation in R8 without assumption of spherical symmetry, add the nonlinear term and proceed with energy estimates, and then use an appropriate cutoff function to go from the R8 to the periodic case, tau 8. Now, I mentioned that a very important piece of this is find a smooth stationary profile. I will go back to that in a second. So self-similar setup, just for, this is just one slide, I'm not gonna say more. You rewrite your V, which is the velocity, which would be the gradient of the phase if you want, and you rewrite the density, you rescale in a certain way to make the equation look much better, so that's the sigma, and then you write with the self-similar coordinates. So this is now gonna be my space coordinate, and this is S. Of course, what R is, well, it's something that you have to keep track of and decide what's the best R for you. And when you rewrite in terms of your equation in terms of U and S, you obtain something like this. The green part is the one that's the fluid-like, and this pink part is the one that you get extra when you look at the NLS, which is very, has a lot of derivatives, so it's not obvious how to control it. But certainly one thing that you want to do is to make this to be decaying. So certainly a condition is 4 minus 2R negative. And I mentioned that the very important thing is to find that smooth curve in your phase portrait when you look at the stationary solutions. So this is courtesy of Caola, Bora, Gomez, Serrano, Buckmaster. And non-smooth things were already found by Gormley, but Merle and all, and then later Caola, Bora, Gomez, Serrano, had to study this kind of phase portraits. And for example, very simply put in this case, you need to find a curve, a smooth curve, that goes from P0 to P infinity, right, through this point here, which is a very singular one. And for this, Caola, Bora, Gomez, Serrano, and Buckmaster used computer-aided proof. All right, so now when I was reading this kind of papers and collaborating with the list of people that I mentioned, I was talking with a friend of mine who is a physicist at Politecnico di Torino, Daniela Tordella, and I asked, is there a physical phenomenon in which you can see this blow up? I really want to see it. And she thought about sonoluminescence. So this is the process by which light is made from sound. So you send sound waves in a liquid with high enough frequency. They cause bubbles that implode in a process called cavitation and produce lights. So this is a little bit of a cartoon. You have a little bubble. You send wave at a certain frequency, and there it pops the blow up, what I think to be the blow up. So the dynamics of the motion of the bubble as a first approximation is characterized by the Rayleigh-Placet equation. And this is derived from the Navier-Stokes equation, the spherical coordinates, and describes the dynamics of how the radius change. So we thought about that, whether we could find a connection between this sonoluminescence kind of phenomenon and the blow up. And well, here you see, I'm only the messenger, okay? If you see something wrong with this graph, it's not me, I didn't do that. But anyway, in this graph here, you see this, how the R, the radius, this was using the equation that should describe the radius of the ball. This is the density, and down here is the velocity, R dot. And here you see the blow up. Right? This is exactly how it blows up. And this is the numerical version of the solutions. And it turned out that, well, in the first time of the blow up, again, this is the velocity, the solution from Rayleigh-Placet and the curve that, according to Daniela, is obtained using NLS, which means nonlinear least square approximation, because I had no idea what that meant when she told me. So there is an incredible, very good match here. And this type of behavior corresponds, you can write it as a ratio like this. And this alpha k that we found were the alpha k that met the conditions on the paper of Merle and al. So, but then when we go to the next jump, the fitting is a little bit worse. So this one, the continuous one, is the one that should go like a power, and there is a little bit of a mismatch, and so on. But I thought this was very interesting because I really wanted to see an example of this blow up. We are finishing writing a paper. soon. And the last bit, I don't know how much time I have. OK, great. So the last bit of this is the rogue waves. So I will quickly go through this. This is work with Massimiliano Berti, Riccardo Grande, Alberto Maspero. And it was, as I mentioned at the very beginning, it was came after some talk that van der Heyden gave on a paper with Matthijs Grafke. And the rogue waves in here is considered to be a rogue waves if the height of this wave is at least twice as much the height of the what is around it. There are two theories. One is, and this thanks to the Quanta magazine, which is, we know is connected to the Simon Foundation, the linear addition. So these are basically linear solutions that come together in a certain way that in a sense, gives you the rogue waves, or something coming from the nonlinear focusing. But in any case, if I'm thinking of this to be the graph of the profile of my ocean, just this is one dimension, the conjecture is that this NTX, if it follows a Gaussian distribution, then the probability should be of this type. So the probability that the wave is 2 times the sup of the wave is greater or equal than h is e to the minus h squared of h sigma. And with Berti, Grande, and Maspero, we actually fixed a small, relatively small torus of circle if you want. And then eta tx is the free water wave surface with smooth random initial data, eta omega 0x, distributed as a Gaussian random variable with 0 average and standard deviation. And we have a sigma much less than 1. Then for h between sigma and 1, in a time length of h to the minus 3, we have this probability, which sort of matches what the physicists had done. These are the last remarks. So the condition h0 be much less than 1 correspond to the weakly nonlinear regime that we can control, in which we can say that there is a solution. The time being less than h to the minus 3 is the time in which we can actually prove that there is a solution for the equation itself. And the main difficulty in proving that this evolution of this Gaussian from the beginning, it's controlled when we look at the profile, is that it does not necessarily remain Gaussian. So there is a lot more to do. So I think that it's hard to tell how much time do I have? I'm done. I don't know if I can take 2 more minutes. Just I'm finished. OK, great. So the difficulty is that we don't see the Gaussian remaining we don't expect actually to happen. So let me just give you an idea of the proof. So if you don't want to go too far in time, so you look at h0 to the minus 5/2, then this, it's much easier to look at or to understand the probability, because we can construct a sufficiently accurate approximation of the solution that propagates Gaussianity. So this is a little bit the same type of thing that we did in our first paper with Garrido, Grande, and Kuriaski. But if you want to reach h to minus 3, then you have to really think a little bit outside the box, and because it's too far in terms of time length. And we have to, we would like to synchronize things. And in order to do that, we use a probabilistic version of the Brouwer's fixed point. But the probability of this event to happen is 0. So you have to do some perturbation of that. And in order to be able to do this perturbation, we have to use some Lipschitz estimates. In any case, the conclusion here is that, at least for the proof that we give, in those two theories that I mentioned before, one that says that are the linear waves that get together, and the other one that it's more due to focusing nonlinear, the first one is what holds for us in this regard. This is the dispersive focusing. And thank you.
Thank you, Gigliola. Do you have any questions? Yes, please.
So for discuss the result on the waterways, what model are you using? What gravity and Kepler?
Gravity, yes, is the gravity one that Berti, Feola, and Pustateri looked at to claim that there is at least a solution using normal forms and all of that. So it's the same system. And I think it's the same the one you use with Fabio and with Yudeng. Yeah, it's that. So in a way, that's the, here I didn't have much time, but Alberto mentioned that during the talk of the PIs. It's a complementary situation of what you have, right? So you can control the L-infinity norm in a large probability space. We are looking at the complement of that, and that's when the L-infinity norm grows. So the two things, in a way, I wouldn't say they are exactly complementary, because we were discussing about that with Fabio, but that's how you should see.
Any other questions? I have a question for you about the implosion,
yes.
The sound implosion. What are the equations exactly? You just had a name for them associated.
The Rayleigh-Placet?
Yes.
So that is a simplification of the wave, the Navier-Stokes equation, and it captures the same type of profile that govern all of this implosion, right? Because NLS, Euler equation, and Navier-Stokes, and so on, at the end, that same profile is the one that you use to pass a perturbation to be solution of all of this. And the equation of Rayleigh-Placet comes from those kind of equations. So it should be, that's why we found some matching, yeah, for that.
In cavitations, normally what happens is that the pressure drops to a certain level and there is a vaporizing happens. And I'm just wondering if there's like a type of a similar things that is happening in your equations.
Yeah, so you are asking a question that my friend physicist is very much debating with me about, saying that the equation that we look at are too simplistic. They should be having a lot more pieces and all of that to look at. And I keep telling her that it's too hard, and this is all we can do. So sure, I mean, one should be changing the system of the equation that we're looking at and adding more things. But as for now, I don't know how to do that. Yeah, it doesn't really. It's not exactly that phenomenon, but it recovers it as a first approximation. And for me, it was interesting to see an example of it.
Yeah, I just had a clarifying question. What were your alpha 1 and alpha 2 parameters in the nonlinear Schrödinger equation?
Right. So the alpha 1 and alpha 2 were the periods of the periodic data, boundary data.
Okay.
There are two directions. I'm looking just at two dimensions here. And alpha 1, let's say, is period on the x-axis, and alpha 2 is the period on the y-axis. And then might be different, and the ratio is what's important.
Okay.
I'm sure that, yeah. About the cavitation problem, so in the physical problem, yeah, there's a little bit of gas in the bubble, but it's basically almost a vacuum, so you have this extremely violent collapse. Yeah. So you say your system is too simple, but actually, if you can make a vacuum in your system, just have no wave function in some kind of region, you're very close to what this is. So I don't know whether the equations can deal with that, but I think they can, right? And so that's really the closest you can get to cavitation, is to have just a vacuum in your 8-dimensional.
I need the physicists to do, and so this is the debate.
You just need to make a hole, right?
Yes, that we are having, and how much more we can put. But it's an interesting question, and one of the sections of the paper we are writing is exactly suggestion to mathematicians of what should be in there and how we should do
just
it.
The wave function should be exactly zero in some finite region, and then you start from there.
Yeah. So in the blow up of the NLS equation, was it on L-infinity norm, right?
Yeah.
So do you know if it is in infrared or the ultraviolet where you expect the blow up to take place?
I don't know how to answer that question.
Well, small k, high k.
Okay, so some experts here that might say, I didn't check where the blow up, so it concentrated it's more on the physical space, concentrate that's what I have been looking at. exactly.
point. So
like
it will
this.
be high K
It's a
then.
self-similar that goes in the physical space. Yeah, I don't, yeah. Yeah. So I see all in the self-similar physical space. And that's, in a sense, once you prove that there is no radial symmetry, you can periodize because of this concentration.
So no connection with condensation in the terms
No,
we
that's
physicists
a bit,
do.
yes. Yes.
It's local.
Yes,
Yeah,
it's
I
local.
got it. Yeah, I got it.
Yeah. Gigliola, thanks for the great talk. It's really just a clarification about the fact that you proved that theorem in 8 dimensions, but then the example that you mentioned it has 3 dimensions. So if you believe that this would hold also in lower dimensions, but it's too difficult to prove, or
Very good question, thank you. So as for now, the type of argument that was introduced by Merle and all, and then we did the non-radial and so on, we believe it will break down in dimension 4. Maybe 4 we can do, but not below that. Yeah.
4 the equations can do it. 5.
Yes, okay. The method. That's what I'm saying. No. I'm saying, okay. You have to, so let's say, you have to always adjust the nonlinearity, like, and I wasn't thinking about that, to make it supercritical, energy supercritical. But once you adjust that, the lowest dimension in which we think we can do, it's maybe the critical one is 4. Below that, we cannot do that. But it has to be always supercritical, otherwise we know that. Okay, maybe dimension 5. Okay. Thank you. When you have a P, I need to check a worker. No, I'm saying you have to change the P.
Oh, you don't change. Okay, yeah.
No. You have to, if you are talking just about dimensions, how far down you can go, you have to change the P to make it supercritical, but the lowest we can do, we think it's 4. That's right.
Hello. Okay, thanks, Gigliola. So I had a question about the large deviations estimate. You said you were working gravity waves, I believe infinite depth. And so would you expect that the methods might also can hold for finite depth or even shallow dispersion relations?
Okay, first you have to make sure that you have solutions that go to a certain time and so on. And then maybe, where is Alberto here? Alberto, I don't know if you want to add something about no infinite depth. Yeah, until you have, yes.
On shorter time scales, probably yes. Yeah. The method is robust.